Well, hello there. I'm Ray Myers. Welcome to Craft versus Cruft. Today, I'd like to show you a talk I've been working on called Preventing the Worst Bugs. I currently work as a site reliability engineer on the platform team at Dividos. I do not speak for my employer. However, we are hiring. You can also find me right here on the Craft vs. Cruft YouTube channel. I'd love it if you were to leave a comment or subscribe or tell a friend. And I am Lambda Apocalypse on Twitter. We're going to look at some case studies from some of the most expensive bugs that have occurred in history. And we're going to talk about what sorts of practices could have prevented them, and then how we can take that information and actually apply it to the challenges we're seeing day to day, you might be seeing day to day, in order to make your environment safer. So what do we mean when we talk about a bug? What I've heard some people say is that a bug is when code doesn't do what the developer intended. That's a perfectly serviceable definition. Someone else might say slightly more generally that it doesn't do what was intended, a matter of whose intention we're talking about. There's an even more general definition that today we're going to use, which is due to Arlo Belshee, who I tend to cite a lot, you might have noticed. Anything that would frustrate, confuse, or annoy a human and is potentially visible to a human other than the person actively writing code. So, we don't like those things. What can we do about them? How do we stop bugs? Well, let me ask you this. When do we fight fires? Certainly one time we fight fires is with a fire extinguisher or a fire engine once they have started and gone out of control. But let's think about a particularly egregious example. What we see here is the Great Chicago Fire of 1871. Why hasn't there been another of those? Why hasn't all of Chicago burned down again? It certainly wasn't because we got really good at putting out fires. It certainly doesn't hurt. It also wasn't because we all agreed we were going to be very careful not to knock over any more lamps. We don't have things of the scale of the Great Chicago Fire of 1871 because of building codes. We fight fires, the worst fires, the most fires, when buildings are constructed. And that's the difference between catching bugs and preventing them. Mitigating an unsafe context versus actually making your context more safe. So, as we look at these case studies, these are the rules we're going to use in the game today. We're not going to say, be careful. We are careful. The people in these examples were being careful, and they did the best they could with the information they had at the time while operating in an inherently unsafe context. We're also going to assume that the tests missed it. You should test. None of this is to say you do any of these things instead of testing. There's a lot of different kinds of automated and some manual tests that are a good idea to do. And with perfect hindsight, the right test could catch about anything. But there was extensive testing in most of these contexts, and yet it was insufficient. So we must think about how to prevent these bugs another way than that. We also want to apply systemic fixes. What could we do in our practices just day to day? And again, not need to think about, well, if we had perfect foreknowledge, we would know how to fix it in this one case. We want to apply this to categories of problems so that this will actually be useful in something we could take forward. So, the miracle of space travel.
Tous les paramètres propulsifs sont normaux et la trajectoire est normale.
37 seconds into the launch, the onboard computers decided 501 was 90 degrees off course. They made a
not our finest hour. So you've just seen the Ariane 5 rocket, and it turned 90 degrees in the wrong direction after launch, triggering the self-destruct. This ultimately was found to be due to an overflow on a 16-bit signed integer that a larger value was being put into. The reason the value was larger than had been previously tested with is that particular component was developed for the Ariane 4, which did not go as fast, and so the input, it so happened, did not need to be as large in that situation. Now, what makes this particularly painful is that the value in question wasn't actually used in the code anymore in the 5, but nonetheless the calculation was still in the code, and the exception wasn't caught because exception handling would have presumably had an impact on performance. And this all tallies up to a loss of $370 million in 1996. So what could have been done differently to prevent this category of problem? Before I get into some examples, maybe you'd like to pause the video and think about it for a little bit and see what you might recommend. So here's some things we could do. Ultimately, an integer overflow is one category of type safety issues. So you could configure your compiler to be more pedantic about implicit casts and be a little more critical about those situations. You could decide when you're dealing with certain kinds of values like distances, you're not going to use primitive types, you're going to use wrapper types, so you can be a little more conscious about what values you're going to represent them with, or have size conventions like maybe 16-bit signed integers just shouldn't be used for these categories of values. Another thing is no dead code. There's a tendency to hoard code long after it's needed, and at worst, it can have these catastrophic results. At best, it's just going to be there confusing you. So perhaps using a linter or just your team's conventions, you might decide you're not going to have any more dead code. Let's look at another example. Going just a few years later to 1999, the infamous loss of the Mars Climate Orbiter costing $150 million. Now, it lost contact while entering Mars orbit due to a mixed use of English and metric units. A lot of times people quote this as an issue converting kilometers to miles. It was actually pound-force seconds to Newton seconds, and it was a component developed by Lockheed Martin in communication with a component developed by NASA. So this was an integration bug. Both of those components were themselves probably functioning as intended, but the integration was where it went wrong. So what could we do about this one? Well, again, we might try using richer types to encode our domain. So if we're passing around a value that's a distance, or in this case, a unit of impulse, force times time, letting the type system express that can reduce these kinds of implicit assumptions. We could also, if there were reasons why it was difficult for us to do that, simply use naming conventions. Say that, we're never going to store something in something that's just called a time interval. It's always going to be like interval seconds or interval minutes, and you're much more likely to understand that something is happening wrong if you're setting interval seconds to a value called interval minutes versus if you are just setting something called interval to a value called interval. So let's go into the financial sector to Knight Capital Group, another one you may have heard of. This was in 2012, and the loss was $440 million that occurred over the course of just 30 minutes due to some algorithmic trades run amok. And Knight Capital Group was the largest equities trader in the U.S. This was due to a number of factors, kind of a perfect storm situation, where a partially failed deploy left old code in place on some of the nodes that it was deploying to, and it wasn't clear that it had only partially deployed. And then a feature flag was turned on that was reused from a name that had been previously used. So this old experimental code that was thought to have been removed was reactivated by that reused feature flag name. causing this issue. How could we avoid something like this? So, obviously deployment validation is a no-brainer. You shouldn't have a release process that leaves any doubt as to whether it fully completed. You could also look at doing progressive rollout. If you've got a situation where you're activating a feature flag with very high stakes, you could certainly look at activating it just partially as you go, or activating it for just a test user that isn't buying real securities and observing it for some period of time. Again, we see dead code just lingering around in the code base for long periods of time being an issue. You can certainly decide you're not going to do that, and especially not have dead feature flag invocations sort of sitting around in these if statements. Feature flags that accumulate are technical debt. You want them to be coming out at least as rapidly as they're coming in. This is also a case of a name collision. Perhaps you can be sure that you're not going to ever reuse the name of a flag. And for one more, let's go far back into 1962, the Mariner 1 Venus probe. A loss of only 18.5 million, but adjusted it's well over 100 million. This, similar to the Ariane 5, veered off course after launch, and the emergency self-destruct was used. This has been referred to as the most expensive hyphen in history. Wasn't actually a hyphen, it was an overbar. So before the coding in question even took place, there was just a mistake copying over the equations in the specification. And as a result of that, the transformation you see at the bottom here happened, and the smoothing function indicated by that overbar was skipped. So when this radius was passed to the navigation system without going through the smoothing process that needed to occur, that confused the navigation system and caused this problem. This one's hard. What can we do? I don't know. We don't trust the spec, maybe? I've got a picture there of a spec being burned. Don't actually burn the spec, but maybe treat it with some level of skepticism. Know that mistakes don't strictly occur after that point, right? That's very much like be careful kind of advice I talked about earlier. Kind of hard to take action on that. Perhaps there's a review process that could be dealt with for specs, though presumably they had one. I don't know the details of that. Richer types, maybe. If you know that a certain area needs to be past something that is a smoothed distance rather than just a distance, maybe you could express it there. Based on what I know about this one so far, the only item I could really stand behind is ambiguous notation. Avoid situations where things can be easily confused for other different things. And so you could imagine using a notation for the smoothing function that had a big old S next to the R or something that wasn't just like collecting these dots and bars and stuff to modify the variables. So that's something that could be considered, I think. So if we put just these four examples together, what are some things we might have learned? Well, in three of them, actually, ambiguous naming was some component of the issue. So names are a huge source of confusion, or can be a huge source of insight if chosen very well, and that's very underrated. So that's something we can definitely take away. Also, no dead code surprisingly shows up in half of these, right? We can assure we don't have dead code sitting around by our habits as enforced by our code reviews. Also, linters can automatically scan for this sort of thing, and I think that's worth doing. We can also express our constraints in the type system more effectively, and obviously we want to have validation on our deploys. Anytime you've got automation that's capable of doing very powerful things, it also should have equally powerful checks on it. And this is all really good advice, but this is not really the lesson, because your needs are unique. You have a particular set of problems right now, and what we've just done here is an exercise in safeguarding, essentially, which is like root cause analysis for bugs. So we will ask the question, what made the mistake likely? What made it hard to detect? What made it hard to fix? and we'll think of small improvements we can make in a relatively short amount of time and execute some of them, and then just regularly repeat that process. And so the thought process we've just applied to these examples, you can apply those in your day-to-day, whether these bugs led to a giant costly loss, in which case, definitely a good idea to analyze them, but even if they just led to some time and troubleshooting. That's where a lot of our time and brain cells end up going in this line of work. What if we were able to spend 10% of our time making things a little more safe and a little more productive? Would that be worth it? Let's suppose that our habits cause a 0.5% change every week, either in a positive or a negative direction, because as complexity comes into the system, it's going to change one way or the other. I can about guarantee that. It won't stay the same. So if we go up by 0.5% each week, over the course of a year, you've gained almost 30 points. If we're creeping down by that same amount, then at the end of 1 year, we'd be 77% as productive as we were in the beginning. So between getting just slightly better consistently and just slightly worse consistently, there's almost a 50-point spread over the course of just 1 year. Your mileage may vary, but that's an illustration of the power that continuous improvement can have. So I'm going to leave you with these resources, the safeguarding exercises proposed in a little bit more detail in this article by Arlo Belshee. These are all going to be in the description, by the way. There's also a talk I very much enjoy called Bug Zero. The Technical Debt article series by Chelsea Troy is some of the best writing that I've seen on that topic. The Test Pyramid article by Martin Fowler is a good introduction to that. In lieu of the Test Pyramid episode, I will inevitably make, worth checking out if you're unfamiliar with just different levels that tests can function at. And something very thought-provoking is Null, the $1 billion mistake given by the person who actually introduced Null into Algol, where it then spread into virtually every modern programming language, except arguably for Haskell. Well, thank you very much for joining me today. Feel free to subscribe, leave a comment, let me know what you'd like to hear some more about. I'd be happy to go into some more depth on any of these topics. And sometimes I think I should find a new way to end my videos, but then I remember what Lao Tzu said in the Tao Te Ching: with patience, the most tangled cord may be undone. Thank you.